Okay, so earlier this evening I was helping a student in Math 253, and she asked about a particular problem, so I thought I would share that with you. So in this problem, we were looking at two planes, one that was x plus y plus z equals 1, and the other, which we were going to intersect with, is x plus 2y plus 2z equals 1. And the question asked, given these two um, planes, can we find the parameterization of the line of intersection? And so um, I approached this problem in two different ways, mostly to try to uh, have the student start to better understand a little bit of the geometry of this and how to use vectors in talking about the geometry. So the first thing to note is you could, of course, solve this pair of equations using the techniques you learned in Math 152. You have two equations. They're not just simply multiples of each other, and so they have a certain amount of independence. And if you think about the geometry we've learned, so you know something about the normal vectors of the two. One is 1, 1, 1, and the other is 1, 2, 2. And so these normal vectors are not pointing in the same direction. And so these two planes are not parallel, nor are they coincidental. So, in other words, they aren't the same plane. And this means that you don't have the situation where you have no solution. The intersection is an empty set, or the intersection is everything. So if you have two planes that aren't parallel that intersect, they do intersect in a straight line. And so the question is, how do you find parameterization of that line? So let's give a little bit of thought to the geometry here. So here's one of the planes, for example. And we can think about the other plane sort of intersecting um, here. And there we go, something like that. It's not such a bad drawing, maybe, given. And so here's this line of intersection, and we want to find an equation for that line. And so there are a number of ways to approach this problem, and we did approach it two different ways. So I'm going to start with what is the more kind of think it through from the geometry without worrying about fancy vector sorts of things, but still thinking about this in terms of vectors. And so let me switch colors here. Um, and so, for example, if I can find a point on that line and then a vector uh, which we could call v, for example, which gives the direction of that line, then I have an equation for this line, so the parameterization. And so let's imagine that point. So here's some origin in the system, and see if I can draw this point. Being some point on the line is, say, given by x naught, which has some coordinates, and then I have the direction vector v, and so I can think of this line L, which is, let me give a slightly different color here. So here's the line L passing through here. So here's L, and L has a parametric representation for some parameter t. It's, well, if you look at this, points on here, L points to some point uh, on the line, and it's gotten there by go to x naught and then travel along in a direction v, some multiple of that length, if you will, and either one way, or if it's negative, the other side of x naught. So, and the way we write that down is x naught plus t times v, and here t is the whole line, so it could range from minus infinity to plus infinity. And so we need to find x naught. We can figure out x naught, and if we can figure out v, then we have this set up, and from it we can draw parametric equations. So finding a point x naught is just finding a point that's in the intersection of these two things. I did it by inspection. So for example, I said, let's imagine x is 1, y is 0, and z is 0. That's certainly a point on this plane. And if I look at this one, I've got x is 1, y is 0, z is 0 as a point on here. So for example, I could take x naught to be 1, 0, 0. That's a point, and I identified it by inspection, if you will. I also look at this. There are then a number of things that one could do. I first imagined, well, the other way to get the, to know all there is to know about a line is to know some other point. For example, x1, which I won't draw the arrow to, but some other point in the line. So if I know 2 points on the line, then I know its direction. And in fact, I know everything there is to know about the line. So if I could, by somehow inspection, find a second point, then I'm moving along quite nicely. So one of the things when I look at these two equations and compare them, I realize, oh, I've got x plus something equals 1, and I've got x plus something equals 1. Certainly these two somethings all together have to be the same. And so I've got y plus z is twice y plus z, and that can only happen when y plus z is 0, if you think about it a little bit. So in order to be in this intersection, I need y plus z to be 0, and in which case x has to be 1. So for example, if I let y be 1 and z negative 1, so the point x1, if I look at it, I could let it be x is 1, y is negative 1, and z is 1. And that works out in both of these equations. So this is also a point on the line. And so I could take v is just simply the vector that connects x naught to x1. And so I could take, that's the x1 minus x naught. And so that's equal to 1 minus 1 and 1. And then x naught is 1, 0, 0. And so this is then 0 minus 1 plus 1. So this tells me, in this case, that L is then x naught, which is 1, 0, 0, plus t times this vector 0, minus 1, 1. And I can write that as 1, then minus t plus t, for example. Which is, I can also write that as x equals 1, y equals minus t, and z equals t. So there's a parametric representation here. Let me just clean it up just a little. I'm still getting used to this new gizmo that I'm using. There you go. There's my minus sign. So here's the parametric equation of that line. It's fairly straightforward. On the other hand, so that relied on me, this solution, very nice geometric solution, kind of relied on me thinking about the problem in the geometry. Notice that, I had to guess 2 points on here and so forth. We also know if I could figure out, so this is the line is defined by 2 points solution, if you will. I might also want to say, can I find another solution where maybe I only knew 1 point, I didn't guess the other? Can I figure out the direction of this vector v without having to guess a second point? And the answer is yes. So if you think about it, so let me see here. Let me save that. Example 1. I'll just stick it on the desktop. So in this case, so let's imagine now that here's my solution. If I want to think about my intersection of two planes again, and sorry, just trying to, this is what you get when you're watching an aphantasic person draw. It's all very mysterious to me. Anyway, I have this line, and I'd like to find a vector that starts somewhere here and points along the line. And what I have in defining a plane, if you remember, is what are the vectors I have associated with it? Well, I've got two normals, one sticking out of plane 1 and one sticking out of plane 2. And so the points in one of these planes, so I've got, again, the two planes, x plus y plus z is 1, and I've got x plus 2y plus 2z is 1. And the two normals, so all of the points in this first plane are normal to the vector 1, 1, 1. And all of the points in the second plane are normal to the vector 1, 2, 2. And therefore, all the points in this line are in both planes, and so they must be normal to both of those vectors. And what's the vector that's normal to two other vectors? Well, we get it by the cross product, right? So of those normals. So here, if I have normal 1, and that's 1, 1, 1, you can just read it off from the equation. Normal 2 is just 1, 2, 2. Then if I look at normal 1 crossed with normal 2, I can look at, so I can have I hat, J hat, and K hat, our usual mnemonic game here, this strange kind of determinant. And let me draw that just a bit better. Kind of getting the hang of it here eventually. So there's I hat times 2 minus 2 is 0, and then minus j hat times 1 times 2 minus 1 is 1, and then plus k hat times 1 times 2 minus 1 is 1. And so if you look at this, this is our vector v, same idea. And in fact, it turns out to be, I can write this as 0, -1, and 1. That looks familiar, and it should. So we've at least got the same direction as we go. And we also know then that, again, um, you know, x naught being 1, 0, 0 is on both planes. Same reason as before. And so this time L, and let's call it S. It's going to be um, the same parameter really, but I want to compare the two. I might have ended up with this vector in the other opposite direction, for example. So if v is a vector that points in the direction of this line, so is minus v. So here I have 1, 0, 0 plus s times 0, -1, and 1. And here, again, s is between plus and minus infinity. And so this tells me I get exactly what I expect. I get x equals 1. Oops. I'm a little tired here. It's getting late. Y equals minus s. And z equals s, where s is, well, a real number here. So here again is the same parameterization. I used s instead of t. It doesn't make any difference. But again, a geometric argument, but one that looks at normal vectors and says, oh, this vector in the straight line has to be in both planes and therefore is normal to, each of perpendicular to each of the two normals that define the planes. And so the vector that gives you that is this cross product. So again, another geometric argument. This one is some people will find more straightforward. The other one I kind of like because it makes you think about straight lines in your usual kind of old-fashioned way to do it. So um, this is just an example, and I'm just doing a little experiment in posting such examples. I sort of didn't realize till too late I could have recorded my session with the student I was talking to, but I'll do that sort of thing next time. Hopefully this is useful to you.